Good morning. My name is Zoe Bass, and I'll be presenting this poster about acetylcholine receptors and their involvement with different paralyzing toxins. We'll be referencing a lot of images and information from the paper by Yves Bourne, Crystal Structure of a Cobra Toxin Acetylcholine Binding Protein Complex Reveals Essential Interactions Between Snake Alpha Neurotoxins and Nicotinic Receptors. Okay, jumping right into the purpose and the theories and questions behind this paper. So different neurotoxins found in snake venom, such as bungarotoxin and cobratoxin, have the ability to bind to different acetylcholine receptors in the body already, and we know that. They bind just like nicotine would, and they have pretty high affinity and selectivity and act as agonists for these proteins. Moving forward, we want to kind of take the information we already know about how they bind with the proteins and kind of highlight the structures and how this exactly works to move forward and maybe have different drug uses and use their conformational changes in the ligand binding pocket to solidify how exactly these molecules are binding and move forward with that. Based on other different molecules, we know that muscle nicotinic receptors have different resting and open states with different affinities for acetylcholine and their other agonists. And neurotoxins can stabilize some of these conformations. And specifically, bungarotoxin, we do know causes conformational changes of acetylcholine, and that acetylcholine has occluded binding sites when some other molecules bind. And we want to see where cobratoxin kind of aligns with that, or if it doesn't. And then we do already know that the cobratoxin binds fully to acetylcholine binding protein, and we'll jump in a little bit and kind of look at how that looks. So we, again, know that binding any molecule changes these acetylcholine receptors. Looking down in this bottom corner over here on figure 7, this is actually a page display of elution for different acetylcholine proteins with varying amounts of cobratoxin. So you can see as they move down towards that anode in lanes 2 through 6, those are the lanes that actually have cobratoxin, and it reduces the mobility of the protein in this page solution. Gel filtration found that the pentamer also has monomer and dimer forms. So looking over here in figure 2, it's very common for acetylcholine binding protein to exist as a pentamer. However, in this page display, they were put in as monomers, and a lot of them eluted as dimers, and that gives us a hint as to how this toxin may bind, because maybe the rings stack and they overlap some bits of their tails, and so they kind of bind together. Let's jump in on some of these images. There's a lot, and they tell us a good amount about the complex. So in figure 1, this is looking specifically at the alpha neurotoxin, cobratoxin. Its own structure helps explain some of the ways it can complex with acetylcholine binding protein in the first place. Knowing what the ligand structure looks like not only explains its relationship with the receptor, but the way the binding protein itself must kind of look to be compatible with such a molecule. Loops at the C terminus, you can see over with these loops, have disulfide bridges, and loop 2 specifically has a little hairpin loop stabilized by another disulfide bridge, and the tip of the bulb has phenylalanine and arginine, which easily form hydrophobic complexes or interactions with different residues on acetylcholine binding protein. There are positive residues on the accessible surface of the cobratoxin, and that's another good indicator of the type of interactions it's going to be able to make when it's in the binding pocket. Scooting over again to this figure 2, which highlights the pentameric complex. This specifically is a perpendicular view, but then if you also look at it on its axis, then you can kind of see the depth of that binding pocket. The structure of the acetylcholine binding protein also clues us in on its function, and more conserved areas indicate that these areas are specifically involved in binding, because substituting those residues kind of render it useless in terms of it being a binding protein. It's a pentameric protein. As you can see, the different 5 associated subunits, all colorful and everything. Loop C is pretty highly conserved, and 3 specific residues that kind of switch between different subsets of the protein across species or different organisms. Switching those out, you can see different affinities and different toxin selectivities, some enhanced, some decreased. Mutations can cause a decreased affinity for the toxin, especially if it is one of those essential residues. And there is some evidence that adding aromatic residues can cause increased affinity for bungarotoxin. So it'd be interesting to see how it applies to the cobra toxin as well. Over here, figure 3, this is highlighting, again, we talked about earlier, how the toxins like to fully saturate all the different binding sites for the binding protein. And you can see that here, there is one for each subunit. And there is full ligand occupation of acetylcholine binding protein sites by cobra toxin. This is consistent with how nicotinic molecules attach and stimulate activity. Again, they're acting very much like agonists that already exist. There's a specific section found between threonine 155 and serine 155 sections of the acetylcholine loop. And it overlaps with different anti-parallel beta sheets of the cobra toxin. And this provides another explanation for how it might sit down in that pocket. It sits relatively deeply within the binding pocket as shown in figure 5, and we'll hop over there in just a second. And the other interaction site that's pretty stabilized is actually a packing of dimers, kind of seen in the page display. We talked about those dimers eluting. This is stabilized and aligned by arginine 206. Again, so figure 4 shows part of acetylcholine binding protein's loop, and cobra toxin causes it to open pretty similarly to how nicotinic molecules affect the protein. So yeah, this yellow portion down here is the loop, and the cobra toxin stabilizes that loop to be open, which we'll talk about again in a second. Here in figure 5, this highlights the way that cobra toxin axis causes it to sit pretty deeply within this pocket over here. It's really nestled in there. So similar to agonist binding, there are a lot of conformational changes within the acetylcholine binding protein when cobra toxin binds. And that is the main focus of this entire paper, is the specific changes that the protein makes upon binding and how that can be useful information to manipulate it in the future. The C and the F loops that line the binding pocket are displaced, and it mimics the pocket being uncapped and therefore primed to accept more toxins until the protein's binding sites are full. Another change is how supportive residues for the binding pocket get pushed towards a solvent, which is shown in figure 6. We'll jump over there. And it might make sense given how they now have more room to interact with the previously mentioned accessible residues for cobra toxin. However, and this is really interesting, the subunits themselves don't change within the pentameric unit. There isn't support for a previous theory that the proteins, subunits themselves, as seen in figure 2, would undergo some rotation, but that isn't the case. There's actually some more refined conformational changes within these binding pockets, but as a whole, the subunits don't change in relation to each other. So this was another theory for agonist activation. And furthermore, this paper shows that the open loop could be a useful target for drugs aimed to capitalize on conformational changes that induce receptor function rather than this rigid rotation. And I thought that was really interesting because this paper took a lot of previous theories and its own findings to come to conclusions that can move forward without being very definitive. It more ruled out different theories. So how did they do all of this? How did they gather this information on the proteins? They first had to prepare a cobra toxin and acetylcholine binding protein complex to examine. And so they occupied and utilized all 5 of these binding sites and tried to minimize excess toxins in the solution. And they purified these monomers and dimers, kind of seen back in our figure 7 with the page display. And yeah, they use SDS and native page displays to show the formation of complexes on a very rudimentary level, just to simply show how it does in fact complex and move through the paged gel. To collect different data on the specific structures, they packed these interfaces within the pentameric units and use electron microscopy to visualize the crystal structures of the complex and compare it to previously studied acetylcholine receptor data. And then for structure determination, they had to, again, use these electron microscopy structures and determine the position of the cobra-toxin molecules. And then the other 4 toxin molecules were placed similarly around the pentameric units compared to that first one that they used. And then the whole complex was refined and examined again with microscopy techniques. So at the end of the day, all this information taken, what are we gathering from it? So main takeaways and things to discuss about this article were that at the interface of the complex, major interactions involving aromatic and aliphatic side chain residues within the binding pocket of acetylcholine binding protein are very important. And at the tip of it, conserved phenylalanine and arginine residues mimic agonistic molecules like nicotine. There is a distinctive and unpredicted conformation of the acetylcholine toxin complex, and it leads to a figure that resembles the resting state of a nicotinic receptor, and it helps us understand the selectivity of neurotoxins for the entire receptor series for acetylcholine proteins. So structural comparison of acetylcholine binding protein bound to cobra-toxin compared to nicotine and different agonists reveals that there are unique changes that happen just with the neurotoxin. So again, there are some similarities between nicotinic molecules and the toxins, but there are a few marked differences. And it reveals that toxin binding is associated with major positional changes of the C and F loops of acetylcholine binding proteins pocket that border that ligand pocket, and notably the expulsion of tyrosine and some of these disulfide bonds that occurred through cysteine residues. And this can contribute to agonist binding and reflects a unique conformational state resembling one of the activatable states of nicotinic acetylcholine receptors. And then lastly, the orientation and position of these bound cobra toxin molecules relative to the acetylcholine binding protein subunits is consistent with different biochemical and mutational data available on neurotoxins and acetylcholine proteins in general. And so moving forward with the information from this paper and from this study, I think it's just going to highlight the ways that the binding pocket can be manipulated for both pharmaceutical and pathological uses. And we can use different natural findings about toxins and existing nicotinic molecules, and then move forward and utilize those for our own benefit and gain more knowledge about how to utilize these receptors. Thank you so much for listening, and I hope you got a lot out of this poster presentation.